Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is Newton's second law of motion. And of course the previous video was on Newton's first law, so it kind of makes sense that we go on to the second law right now. What we're going to be talking about in this law is a mathematical version of what we discussed in the first law. If you recall, the first law talked about what happens when the forces are balanced on an object. The object moves with a constant velocity. So a natural question might be, what if the forces are not balanced? Well, we know that the object will accelerate, but the question is, how much acceleration will there be? That gets answered by Newton's second law. So in a moment I'm going to ask you to pause the video and have a look at some of the questions we will deal with, as well as where we are in the unit schedule, and also what are the learning goals and success criteria. So please do that now and then return. Okay, and you're back, and let's get started here. So the first slide I'd like you to look at just has a little bit of thinking going on about Newton's second law. We're not actually going to do any math here. What I want you to think about first in the first scenario rather, is the relationship between the acceleration that an object experiences and its mass when we push on it with a force. And so to help keep things simple, as you know in science, we like to control our variables. So what I'd like you to imagine in the game of American football, I've got a few pictures here. One is a guy carrying a ball who looks like a professional football player. Obviously, this is a very heavy person who probably weighs many, many pounds, let's say 225 pounds perhaps. As compared to a little kid who's just learning how to play football, also carrying the ball, this kid weighs maybe 50 pounds, who knows. So these two guys are going to be running, and they are up against the dreaded linebacker. This guy looks like he wants to kill something and eat it, and that is his job in a game of football. His job is to tackle these guys, and he does it by applying force. So these two guys are going to take turns running at the linebacker, and because they're running at the same linebacker, I am controlling my force. I'm keeping the force that this guy over here applies constant. And so here's what I want you to think about. When the linebacker hits each of these running backs, each of whom have different masses, one of them has a large mass, which I'll designate with a big M, and one of them which has a little mass that I'll designate with a little m, what do you think will be the result? By result, I mean the effect or the change in the running player's velocity. In other words, the acceleration. How do you think the applied force will affect the different masses, and how will we measure that effect? By looking at the acceleration. Pause the video now and formulate a response in your mind and then come back. Okay, and you're back, and I hope you thought, well, the really powerful linebacker, when he exerts a force on a heavy player like this, is probably not going to have as much effect as if he hits a really light player. So what we're trying to say here is that the acceleration depends on the force. If there is more mass, actually, sorry, let me check myself there. I'm thinking of the other situation. What I wanted to say was the acceleration depends on mass. If there is more mass for a given force, then there should be less acceleration. Why do we think this? Because when we exert a force on really heavy objects, it's hard to get them to change their motion. It's much easier to change the motion of lighter objects. On the other hand, when there is less mass, the little kid getting hit, there is more acceleration. So what we've got here is what's called an inverse relationship or a reciprocal relationship. So we need an equation that has acceleration going up when mass goes down and vice versa. Can you think of a type of equation that has these properties? Well, we're going to see on the next screen, but just keep that in mind for now. All right, now in the second scenario, a little bit different than the first, this time we're going to look at how the acceleration depends on the force. And as good scientists, we're going to control our variables by keeping the mass constant. Let me show you what I mean. This time, the original professional running back has the ball, and he's running, and he is up against a little kid who's going to try to tackle him versus the same professional who's going to try to tackle him. It's pretty clear that this little kid can only exert a little bit of force on the running back, but this player here can exert a lot of force on the running back. The mass here is, of course, constant. So what do you think is going to happen? What will be this guy's acceleration when he gets hit by the kid versus the adult professional? Pause the video, think about it, formulate a response, and come back with your answer. Okay, and you're back. And I hope you realized here that the acceleration obviously depends clearly on force. Running out of space here, hold on. The acceleration depends on force. How? Well, if the force increases, then the acceleration also increases. You hit something harder, it's going to accelerate more. And if the force decreases, the acceleration will decrease. So this is not an inverse relationship. This is more like a direct relationship of some sort, where if one thing goes up, the other thing goes up. Now again, I haven't told you what exactly the formula is, and in my class, if you are watching from my class and not from somewhere else, we are going to do a lab where we discuss exactly what the relationship is. Just for those of you who are following in the schedule, that is this lab here, Newton's second law, where you're going to learn or discover the exact formula. But for now, let's go to the next screen, and I will give you the formula, because you may or may not have done the lab yet. It looks kind of like this. F equals mass times acceleration. This is a formula where if we just rearrange it, which I'll do in a moment, let me do a little bit of algebra here. A equals F over m. This might be a better way of thinking about it. I'll highlight this so you can focus on this version of the formula. If we think of it this way, this formula has the characteristics that we looked at a moment ago. Since force is in the numerator, when you have more force, the overall fraction gets bigger, acceleration goes up. And isn't that what we said back here? Yes, we said if you have more force, you get more acceleration. On the other hand, in this formula, mass is in the denominator, so when the denominator gets bigger, more mass, you get less acceleration. Is that what we had previously? If you look back, yes. As mass increases, acceleration decreases, and vice versa. So this is the equation version of Newton's second law. Now, of course, you're trusting me that this is exactly what the formula looks like, and there's no exponents. For example, you don't know yet whether acceleration equals f squared over m, or maybe over the square root of m. You don't know any of that. To find that out, you have to do this lab over here, and we will do it in class. But for those of you who, once again, are just watching to learn a little bit about physics and you don't have access to the lab, take my word for it, it's none of this. It is actually very simple. All of these variables are to the first power. But we're not done yet. There's still one more catch, and these two pictures are going to help explain what that catch is. In the first picture here, a young girl is pushing, or at least trying to push, an elephant into some sort of crate, I'm guessing for transport, maybe at a circus or something. Think for a moment, do you think that this girl is going to have any effect on this elephant? Clearly not. She can't possibly exert enough force to accelerate the elephant. It's a situation where she can apply force, but the elephant won't move. It's actually not only because the elephant is so heavy. If the elephant were in outer space or on ice, on a frictionless surface, she would actually have some small influence on the elephant. However, because the elephant is on the ground and because there is friction, she has no chance of pushing the elephant. In fact, what we should do here is draw the free body diagram of the elephant. I'll draw directly on the elephant as a dot. So here is the gravitational force acting on the elephant. Here is the normal force as a result of standing on the ground. Here is the force applied by the girl. And of course, there is friction backward. We've just been learning about this in class. And if you think about it, the normal and gravity are equal. The elephant is not accelerating up or down. And the friction and girl's pushing force are equal, which means the forces are balanced here. Now that's an important thing to consider. When you have forces that are balanced, as you know, this means that the net force is zero. We've already learned this. All right, keep that in mind because it's going to matter very, very shortly. Let's take a look at this next picture here where you have people trying to push a car that is stuck on ice and snow. This is at the time that I'm making this video. It's December of 2013, and very shortly there's going to be a lot of snow and ice, and you might find yourself in this situation. What forces are acting? Well, once again, there is a normal force. I'm sorry, you probably can't see that, so I'll switch colors to red. There we go. Here is the normal force. Of course, there is gravity acting on the car, and due to the fact that the car is not accelerating up or down, these are seen to be equal. Now, the people are pushing forward. Let's call it an applied force, as it's sometimes called. And if you've ever been in this situation before, you know that unlike the girl here, you can have some success. It helps if there's someone in the car who is pressing on the accelerator and trying to help you, but even without someone turning on the car, if the ice were sufficiently slippery, you could actually push a car even if its wheels are locked. So let's just say that there's a little bit of friction, but not enough to stop us from actually pushing the car forward. In the language of physics, we would say that the forces are unbalanced, and so we would write that the net force is not zero. In fact, it is directed to the left in this diagram, so square brackets, left arrow for direction. All right? What is my point? Why have I shown you these two pictures? My point is that you don't just get acceleration for pushing, remember the girl, you do get acceleration for having a net or an unbalanced force. So now we go back to this formula and we put in what really matters to make it truly Newton's second law, A equals F net over M, or F net equals MA. And this, by the way, is the fact of the video. All I want you to do for the fact of the video quiz is just remember that it's F net equals MA, not F equals MA. All right, let's move on. Try a few examples here, some simple but real calculations where we're going to use the fact of the day. Everyone can identify this. This is a sumo wrestler with a little kid trying to push on him. Obviously, it's kind of like the girl pushing on the elephant. Not much is going to happen. However, I bet you he'll have more success than the girl pushing on the elephant. I did a little bit of research and I found that a sumo wrestler can have a mass of maybe 175 kilograms is not unheard of, around 400 pounds. And so I did a little bit of thinking, this boy who, I don't know, maybe he's 7 years old, give or take, what force could he apply? It looks to me like he's pushing with his legs, so I did a little bit of thinking in my mind. I imagined if you gave a kid something to hold and maybe squat down and then lift up using only his legs, how much force could he exert? And I guessed to myself, I don't know, he could probably hold maybe a 35 kilogram box, close to 70 pounds. Maybe he could use his legs to lift this. And so I guessed he would have to apply a force equal to gravity with his legs of at least mg, at least 35 times 9.8, which is approximately 350 newtons. So I just guessed based on this that maybe this kid is capable of exerting 350 newtons of force on the sumo wrestler. Now, there is friction on the sumo wrestler, which we would have to take into account. This question is also kind of tricky because the sumo wrestler could actually tip over due to the fact that the kid is pushing high up and the sumo wrestler is planted on the ground down here. So to keep things really simple, let's imagine for a moment that the sumo wrestler is on ice, so that there's actually no balancing force, and this is therefore the net force. What would be the acceleration of the sumo wrestler? Well, it would be A equals F net divided by the mass. And so you would simply plug in 350 newtons, which in this case we could say is forward in direction, divided by the mass of 175 kilograms. And what would we get? 350 over 175 is 2. Now, the units look like newtons per kilogram in the forward direction, but as you also know, acceleration can be written as meters per second squared, so these are equivalent units. Either or is just fine. Okay, there's a simple example of Newton's second law. In this picture over here, we have a picture of a drag racing car. These are the fastest drag racing cars that there are. It's called top fuel category. There's different categories for drag racing. I did a little bit of research and I found that the mass of these cars can get up to around 1,200 kilograms. So they're about the same mass as your typical small car on the road these days. They want to keep the mass as low as possible, of course, because they want to accelerate very high more mass does not help with your acceleration. I wondered, what is the acceleration of these kinds of cars? Well, to find the acceleration, I had to dig a little bit. I found that they can go from 0 to 500, sorry, not 500, but 450 kilometers per hour in about 4.5 seconds. So then I did a little bit of math, and I've unfortunately forgotten the exact numbers, but I'm going to get out my calculator right now. I'm going to convert this to meters per second by dividing by 3.6, so 450 divided by 3.6. I get 125 meters per second. You all remember how to convert from kilometers per hour to meters per second, right? And if I'm doing this, this is going to be delta v over delta t. So the change in velocity is a positive 125 meters per second in a time of 4.5 seconds. What's that give me for an acceleration? I get about 28 meters per second squared, which is a lot. So knowing that this kind of car can accelerate like this, and knowing that its mass is that, what is its F net? What net force can be applied by these engines? Well, let's see. It would be the 1,200 kilos times the 28 meters per second for a pretty impressive, just calculating this now, approximately 333,000 newtons of force, exclamation mark. That is a lot of force that these cars can, these car engines can exert. So there's some quick examples of Newton's second law, just to give you an introduction. And we're going to finish off with one that's a little bit trickier here. This is more of your textbook example, so let's have a look. A brick of mass 2.5 kilos is sitting on a horizontal surface. They start telling me stuff, I start drawing. Here we go, horizontal surface, brick, very good. Write in m equals 2.5 kilos. The coefficient of friction, remember that, that's mu, 0.44. Determine the magnitude of the acceleration if a horizontal force of 19 newtons is applied on it. So let's imagine that someone is pushing on this block, and the force exerted is not a lot, but 19 newtons, and the way I've drawn this, that is to the right. Okay, now, they don't come out and tell you exactly, but I think you can figure it out. There is a friction force here. After all, there's a coefficient of friction. So we know that backward going this way is FF. Now, stop for a moment and think. Is FF equal to 0.44 newtons? This is a very common question that people ask. Is the force equal to the mu value? Pause the video, look back if you have to at your formulas, but actually no, mu is not the force. If you recall, we learned in a previous video that FF is equal to mu times the normal force. So it'll be 0.44 times something. What is that something? Well, in order to figure this out, we got to figure out the normal force. We got to draw a free body diagram. So let's do that. We already have two forces acting on this object. What are the other forces? I'm going to draw a free body diagram to help you see. We said the applied force. We said some friction. You know that gravity is acting, assuming we are on planet Earth, which I guess most of you are. And if we are not accelerating vertically, then by being on a surface, you get a normal force which is equal to gravity. Here's the key to this problem. Fg is equal to mg, which of course is 2.5 times 9.8. And that number comes out to, I'll just plug it into my calculator here, 2.5 times 9.8. I get 24.5 newtons. And by the analysis that I did with my free body diagram, I know this is equal to Fg, so I can also write 24.5 newtons. And now I'm going to use this in the friction formula. I'm going to multiply by 0.44 which gives me my friction force of 10.78 newtons. So now let's take a look at what we've got. We go back to our free body diagram. We have 10.78 newtons going backward. We've got the applied force of 19 newtons indicated forward. Normal and gravity cancel. So remember Newton's second law. Sorry for jumping around there. Newton's second law here, F net equals ma, A equals F net over m. So let's write that out and see if we can't solve this. F net equals ma. What is the net force? Do you remember how to calculate that? We did this back at the beginning of the section on calculating forces. And if you remember, it means you've got to add up all the forces. You've got the normal force. You look at your free body diagram, you've got gravity. You look and you see friction. And you look and you see the applied force. Now, I know some of you are thinking, hey, but wait a minute, some of these cancel out. And you're absolutely right. For example, the normal and gravity cancel. They are equal and they go in opposite directions. Do you have to write them on this line? I think you should. I think skipping these will cost you points sometimes when they actually don't cancel, because they don't always cancel, as we will see later on. So always write out what the net force is. It means just add up all the forces you see on the free body diagram. For the ones that don't cancel, what have we got? We've got 10.78 newtons left added to 19 newtons right. That's equal to 2.5 kilograms times A. Now what do? Are you ready to add and subtract? Not quite. Left and right don't mix. They're like oil and water. Get rid of that left, make it a right, put in a negative there, because a negative right is a left. Now what do you get? Negative 10.78 plus 19, giving you 8.22 newtons of net force to the right, equaling 2.5 times A. And what does that give you for A? Well, divide by 2.5, and you get, let's see, 8.22 divided by 2.5. I get about 3.3 with correct sig figging, and that would be meters per second squared right. One last thing, folks. They asked for the magnitude, so they don't want direction here. Probably the reason they don't want direction is because they didn't mention direction. I just kind of added in my own. Therefore, you would have to finish off by saying A with magnitude, that is the absolute value symbols, 3.3 meters per second squared, and that would be your answer. So we've seen how to use Newton's second law. We've seen where it comes from, that it actually makes sense. To get all the details, you got to do the lab that we're going to do in class. Don't forget the fact of the video, and I will see you in class. Thanks for watching. Have a good day. Bye now.